Well, hello everyone, and welcome to Prep 10. So in this lesson, we're going to be talking about correlation and regression. And the easiest way to understand the difference between them is that correlation tells you how well the points line up to a line. So for example here, you've got a line and there's the points. It tells you how far apart or how well they line up to the line. Same as here. And then regression actually tells you the equation of the line. So as you see here, this equation, the y equals 1.1803x plus 18.852, that is the equation of the regression line. And the reason that's important is because then it allows you to predict future values for which you don't have a point. But we're getting ahead of ourselves. So let's back up and start with correlation, which is, again, how well the dots line up with the line. So correlation measures how closely data points follow a straight line relationship, while regression determines the trend line that best fits those points and can be used for predictions. In this tab, you will see two lines that have the same correlation but very different trend line or regression equations. So as you can see here, well, actually you can't see here yet because we haven't put the correlation on, so let's wait until we do. So let's go ahead and calculate the what's called R, which is the correlation coefficient, using the function CORREL, and then you're putting in the two arrays, and when you put in the two arrays, you put in just the numbers because it doesn't take the column headings. And so our correlation coefficient is 0.72. That label then pops up on the graph here. And we'll do it the same for this one as well. And you'll notice that both graphs have the same correlation coefficient, but the lines have very different slopes. And in fact, the equation of the line is different, the y-intercept is different, and the slope is different for both lines. Now, in terms of correlation coefficients, we always want to interpret them, and based on the strength of the correlation. So, if it is a positive correlation, then very strong is 0.8 to 1. Strong is 0.6 to 0.79. Best way to remember these is just think that you're going basically 20% at a time. So starting with 0 up to 19, so 0.20, and then 0.20, 0.40, 0.60, 0.80. And similarly in the negative direction. All right, one other thing that we're going to have new in this lesson is the data analysis tool pack, and we're going to use it to put the output in the correlation matrix to place it here. And the way that you do that is you go to the data tab and go to data analysis, and that brings up the data analysis tool pack. Now, if you come here and it's not there, then you're going to have to install it. And please see the help section in the class for information on how to do that. Okay, so we are doing correlation. And the input range is going to be, actually let's do it from the first one, though it doesn't actually matter, we can pick either one. Notice that I am selecting the column headings and the data, but only for the columns that have numbers in them, because correlation is all about numbers. In other words, I don't select the first column that has names. I choose labels in first row because I did select the column headings, and then my output range is going to be right there. And this creates a correlation matrix that shows me how things correlate. Now, these numbers sometimes are hard to read, so what we usually recommend with output from the data analysis tool pack is to immediately remove all the decimal places and get it down to 2 decimals So it kind of makes sense. So as you can see here, we see all possibilities. There's the 0.72 correlation between sales calls and copiers sold, and it doesn't matter which one is first, it's still going to be 0.72. If we had used the second matrix, then maybe this one would have been up there, but again, where they meet would still have been 0.72. Days missed and sales calls almost has a zero correlation. I mean, there is something there, like if we expand the decimal points, but not much. And then copiers sold has a negative correlation with days missed. In other words, they move in different directions. As days missed goes up, copiers sold goes down. All right, now let's turn our attention to some of the questions. So what is the increment to move between very strong, strong, moderate, weak, and very weak? Well, it's just what I said, that they move basically 20% at a time. What type of relationship is there between number of sales calls and copiers sold? So sales calls, copiers sold, here's the relationship. And let's see what our choices are. So we've got the correlation each time, and it's a positive relationship. The reason we know that is because the line is going up. And then the question is it very strong or strong? Well, if everything goes 0.20 at a time, then starting backwards from 100, you'd be down to 80. We're at 72, so we're in the next bracket. So we're not very strong, but we're strong. What type of relationship is there between number of copiers sold and sales calls? So now we're in the second graph. And that's also positive and also strong because it's the same relationship. Even though the slope is different, the correlation is identical. In other words, how well the dots line up to the line is identical in both cases. If the correlation is positive, what does that say about the slope of the trend line? It means that it's rising, as in both these examples. And which graph has a larger slope? Okay, so let's look at them. Well, it's clearly this one. And you can actually see the value of slope, 1.18 versus just 0.439. So it's going to be sales calls versus copiers sold. That's our first answer block. Now, second answer block. What variable is associated with the magnitude and sign of the slope of the trend line? So magnitude and sign. All right, so if it's slope, the variable associated with slope is always x, and the coefficient of x will be the magnitude, and then its sign, if it's positive or negative, will also tell you if it's sloping up or sloping down. So the variable would be x. R ranges from -1 to 1. As R becomes more extreme, meaning closer to -1 or closer to 1, what happens to the dots? The dots get closer to the trend line. In other words, they line up with the trend line. R squared ranges from 0 to 1. So what's R squared? There's R squared. It's sitting right here on both graphs. And basically, Excel throws those in for free when we add the trend line equation. And so what is R squared? Well, it's actually this 0.72 squared. You can see it there, and you can see it there. And it has a special name in statistics. So if R is the correlation, then R squared is what's called the variance. So it's the square of R and also called the variance. What information does R contain that is missing from R squared? Well, if you square any number, even if it's negative, you're going to get a positive number. So once we square R, we lose the sign. In other words, we don't know if the line's going up or down. And so that's going to be the direction of the relationship. In a scatter plot, which variables are normally placed on the x and y axes? So here, these are names. So the x-axis, and this comes from science, the x-axis is called the independent variable, and the y-axis is called the dependent variable, and the idea is that x predicts y. And that's it for those questions. All right, now we get to inferential correlation. So this is the same data. So what's the difference? The difference here is we were just analyzing the sample. We weren't saying anything about the population that this sample came from. On this tab, we actually are going to try to make a claim about the population based upon this sample. So that's pretty cool. So an analyst wants to determine if there's a relationship in the population between the number of sales calls and numbers of copiers sold. They take a sample of 10 employees and collect their data. So the case is two-tailed, because it always is, because we don't know which way it's going to go. The distribution is a t-distribution, because we don't know the population standard deviation. The null hypothesis is that correlation in the population, remember, in the population, correlation in the population is 0. And the alternative is that it's not equal to 0. All right, the correlation is that CORREL function. N is a count of just one of the columns. So they're kind of like pairs. Degrees of freedom is going to be n minus 2. And the sampling distribution of R, the mu, the mean of the sampling distribution of R, which is what we're going to plot here, is going to be 0. Why 0? Because 0 means that we have no correlation. And then the standard error is going to be the square root of 1 minus R squared divided by n minus 2. Well, n minus 2 is also the degrees of freedom, so I could just put that in there, but I'll stay true to the equation. N minus 2. Maybe I shouldn't have. So let's see if it happened. So I've got the square root of 1 minus R squared divided by n minus 2 and it's telling me value too high. Usually when this happens, it's a parentheses thing, but let me see, there's square root 1 minus, oh, maybe I didn't get the R squared. In fact, I did. I picked the wrong guy. There's R. 1 minus R squared. There we go. And the observed difference from 0 is basically the correlation. So we'll just put equals correlation. And t is going to be equal to that observed difference, or effectively the correlation, divided by the standard error. And the probability of t, it's two-tailed and it's positive. So it's going to be t dot dis dot 2t. .89%. All right, now we can take a sneak peek at the graphs and start to get a feel for this. So there's our R.72. Remember, we expect, if there's no correlation in the population, that the correlation of the sample would be over here closer to 0. We are more than 2 standard errors out, more than 2 standard deviations. out, and that's usually a sign that we're going to end up rejecting. We don't see the rejection region yet over here on the standardized distribution, but we will in a second once we compute the critical values. So this is going to be T dot inverse probability degrees of freedom. And this would be easier to copy if I lock the degrees of freedom. And T dot inverse, now the probability is going to be 1 minus that. All right. And then for our confidence interval, we'll take the correlation, which is R, that number. And over here, we'll make that equal to R minus the standard error, which is over here, times the two-tailed right. And then go the other side, equals R plus the standard error times two-tailed right. Now the problem that we run into is that this 1.29 is too big because a correlation can only go from -1 to +1. So we're going to have to fix that, but let's first deal with the one that's fine. So the lower bound is just fine, so equals that. But for the upper bound, we can't stay with 1.29. We actually have to knock it down to 1 just by over-typing. So we're just going to type a 1 there, because that's the most it could be. And then that gives us our confidence interval. So in other words, what we would say back to our boss is we think that there's a 72% correlation in the population, but we could be wrong, and our confidence about that 72 goes anywhere from 0.15 or 15% to 100% in the population. All right, let's questions. What is the difference between the dots in the scatter plot and the dots in the distribution graph? So dots in the scatter plot represent rows in the raw data, and distribution dots measure sample R's. As R approaches either 1 or -1, what happens to the graphs? The dots hug the line, so that's true. And the test statistic should become more extreme. We reject the null because something's going on. That's why the more extreme. We reject the null and R is positive, right? More extreme, meaning into the rejection area because something's going on. We reject the null and R is positive. Can we conclude the increased sales causes increased sales? Never use the word causes in this class. The most you can ever say is predicts. We would actually have to create a controlled experiment to say causes. So, no, increased sales might cause increased sales calls, or they both could be caused by a third variable, such as sales promotions. Would correlation be the same if x and y axis were switched on the scatter plot? Yes, they would. And R would be the same. But we proved that on the first graph. The correlation in this test is positive. What would it mean if it were negative? So if it were negative, for the negative, whenever you're asked negative, always look for two words that move in different directions. So this is same direction, increase, 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 decrease, increase. So they move in different directions. So that has to be the answer, because this one is same direction, decrease, decrease. And there you've got it. And that's it for that answer block. So we'll take a break and catch you in the next video.